Welcome back. And I was asked to talk about multi-wavelength astronomy, and Neeraj has already spoken in detail, so I'll be building on what he has already spoken. I come from National Center for Radio Astrophysics, who runs GMRT, which a number of times Neeraj mentioned about this instrument. There was one question from someone that there are satellites and they're going to interact with our telescope. We astronomers are greedy. We want everything from 10 megahertz all the way to many tens of gigahertz, hundreds of gigahertz, and satellite communication lines. They have money, we don't have money, and they essentially buy the band and we are stuck with that. So at GMRT we have an extra facility. We essentially know what satellites show up when you look at certain patch of the sky, and list of all the satellites, at what frequency they radiate, we know that also. So if you are observing a patch of sky at certain band, we can exactly tell you, please flag from time A to time B, channel this, and your data is clean. So I am still greedy. I'm forced to flag a little bit of data. I'm okay with that, but I can fix the problem there. And because it's a pathfinder instrument, it's a good way to learn if you have some thought process. That I have some certain experiment in mind, SK will do it for me, but I just want to explore this thing. So do think about that and do not miss out on that. I haven't planned. I was asked to talk about multi-wavelength astronomy. I'm a radio astronomer. So if you talk to me, as Neeraj was mentioning, 3000 gigahertz and 100 megahertz, two different frequencies is multi-wavelength for me. I'm sitting in radio band only. But I'll put in little effort to understand why it is important. So we'll start with some thought which I have put up over here. So from low energy to high energy, we'll pick up what these things tell us. And then I'll spend some time to understand emission processes. And these emission processes send out energy in certain bands. Mostly we'll be covering. Can we fix this hum sound? Maybe. Can you keep it far? I think this is echoing. I'll take it if this fails. Yeah, so we'll spend little time about emission processes. These are very important when you come to SK or something. Essentially, SK will operate only in radio band. What it can do, we'll focus a little bit about. So bulk of the talk from here to here is more about emission processes, but keeping in mind that we are going to understand multi-wavelength astronomy. I'm a very boring person and I want interaction from both sides. I want to learn from you and I want to tell you what I know a little bit. So these are three images. Can people make thought what are these three images telling us, or why have I put up guesses, serious answers, wild thoughts? Yeah, they are at very different wavelengths. Okay, one more guesses. Yes. Different?
We are trying to use different elements.
Okay, so different images are showing different elements. Okay, two, and yes, you were saying something. Right. Three. Any more wild thoughts? Okay, I'll come back to this thing. We'll take it up. You all know electromagnetic radiation. Fortunately, all the way from radio to gamma rays. If you look at the radio part from here to here, it picks good fraction of electromagnetic wave band. And it becomes very important that if I want to study an object, I want to study it at multiple places. And if I've done substantial amount of it is covered by radio band, I want to thoroughly polish it. Okay. What I have put up in different panels essentially is what is the operating frequency or operating wavelength. Here we are talking of the order of meters, And there I am talking about very tiny micro kind of places. At visible I am already in angstrom regime. I am also putting one more temperature scale below that. What is this telling us? X-ray is of the order of 10 power 6 million Kelvin temperature. Optical is around 10,000 Kelvin. And when I come to microwave, I'm talking about 1 Kelvin, and if I move to 100 megahertz, it's even boring number. I'll show you that. Okay? So, you all have read Wield's displacement law. Essentially, lambda times temperature peak wavelength is a constant number. Sorry. So, object's temperature determines the wavelength at which most of it emission is radiated. And if you look at this little patch over here, so the peak over here is in the infrared, and if I move further, this is 724 nanometer, this is 483 nanometers, which is over here. So peak essentially moves lower and lower frequencies as the temperature rises. Okay, so that's something which we'll be exploring in this talk completely. And we all agree that electromagnetic radiation is everywhere. They essentially, the light we see, I'm communicating with you, I go out, I get sunburnt. Radio waves, which are important for our cell phone communication, or if you are a little old enough like me and you have heard commentary on transistor, that was very important for me, maybe not for now for you. Television signal used to come on electromagnetic wave communications. So it has a property which demonstrates both. It has like wave-like nature, meaning it shows interference, and particle-like nature, which means it has photoelectric effect-like feature experiments. So we'll pick up some aspects of this electromagnetic wave. We'll pick up states of matter. Okay, this little object has this temperature and what it is telling us along those lines. So we have coldest, warm, hotter, and hotter still. So essentially, coldest, let's say temperature of the order of 100 Kelvin. So if you look at astrophysical objects, you will essentially be probing dense molecular gas. I'll give you those examples. If you go to warm, which is of this, these are just a little bit of astronomical jargons. When we say warm neutral gas or warm medium, these are the temperatures we are talking. So we have to live with these numbers. So if you are in the warm regime, then warm dust and molecules is what we are looking at. Hotter of the order of 10,000 to 10,000 Kelvin, we have moved to close to visible band essentially. So atomic gas, molecular, so essentially molecular bonds tend to break down. We are looking at those aspects over there. And if you make it more hotter, 10,000 Kelvins, we have moved to the very high energetic regime, which is kind of close to X-rays. So these are like ionized gas, interactions of ionized gas with the hot medium, etc. So we'll pick up first the radio and the microwave band, which is the largest part of the electromagnetic spectrum. Long wavelength, essentially it can penetrate, your cell phone signal can come inside, whereas sound wave may not be able to propagate outside, right? So most matter is transparent to radio waves. It essentially probes coldest matter, dense gas and dust. It also, like your 2.7 Kelvin, the cosmic microwave background radiation, for which people got Nobel Prize, the Penzias and Wilson, which we just talked about, happened at 2.7 Kelvin. This was in the microwave band of radio. They probe molecular gas also, some of the transitions which happen in the radio band. I'll be talking about it. So essentially many molecules were first detected in ISM of the Milky Way through radiation. Some of the molecules and like carbon monoxide, hydrogen cyanide, acetaldehyde in the center of the galaxy, these are also detected in the radio band. So these are spectral line studies. If I want to move to next regime, which is mid-infrared to far infrared, this is again longer wavelength. Very penetrating, it can reach to longer wave. So these, in astrophysical bodies, they will essentially look at size scales which are comparable to these wavelengths. So the dust grains, when we talk about silicates and those things, So from giant molecules to grains of glass, which are silicates, those are detected over there. Most of the known dust in universe emits mid to far infrared radiation. For example, around dying stars, you will see these dust forms around them. What happens is dust essentially becomes kind of some semi-solid, and so planetary systems can also form because of that. So these are also studied in infrared band a lot. And around when you have massive galaxies, surroundings of that again have a lot of dust surrounding that, and planetary systems, as I mentioned. Let's step a little bit from far IR to mid IR, near IR to mid and far IR. Again, properties haven't changed much. We have three different images. So what you see here is visible, near IR and mid IR of the same source, Horsehead Nebula, and you see distinct features which are seen in one band, not another. This is what you see in visible, and what then dust surrounding it is not seen in visible but will be seen in mid IR and far IR. So if you want to study an object, you definitely want to look at it in multiple bands. Near IR is again similar to other IR bands, mid and far. They again probe little bit hotter gas, dust and molecular gas, somewhat penetrating. So now you can understand I was moving away from radio towards the X-ray side. I'm going to use the penetrating very loosely. Typical frequencies are 2 micrometers, which means it's 10 times the wavelength of visible light. So these probe stars again cools cold gas around the stars, and or stars which have just formed. These are the ones which are picked up by these things. So this is an example of galactic center which is seen in visible, and in near IR, which is 2 meter all sky survey which has been done, this thing over there. Visible light, we all are very fond of, like the moment you put a telescope, what you see is what is there over. And this, as Neeraj was also mentioning, in our Milky Way is dominated by stars. And in other galaxies also it is dominated by stars. Starlight can be detected directly, or it can get reflected from dust grains, so you can see in polarization also the starlight over there. And these are all seen in visible band. In galaxies, as we say, stars are primarily constituents of it, so we definitely want to see those galaxies in visible band necessarily. So distant galaxies are usually first detected in visible or near IR systems. Neeraj also talked about, like, I've looked at the object in radio band. Unless I know where it is located, how far it is, or the redshift information of this thing, I will not be able to do much. And bulk of the time, the redshift information comes from the visible band. So furthermore, gas ionized by ultraviolet emission, which will take it up next, from the hot star and heated to about 10,000 Kelvin also emits brightly in visible band. So these are the class of objects which people look at it in these things. And Orion Nebula is one example. You saw this picture. Next, I am showing you this picture. Essentially, that is optical. This is infrared, and you put together infrared and optical, and the top is what you are seeing over there. So details which you are talking about becomes important, and the moment I am able to do this optical and IR, because both are giving me similar resolutions. But if I want to do this, what optical is giving, and Neeraj talked about in radio, it becomes very difficult. Can you make a guess? My resolution, angular resolution. What is it? Yes, my ability to resolve two nearby objects as two distinct objects. This number for I, let's say, is some x, and if I want to match that x in radio band using GMRT operating at 1 meter, can you make a guess what must be the size of the telescope? Just size of the dish. Wild guesses are also allowed. 1 meter. I am telling you, with I, that's just a half a centimeter pupil size, right? Or operating at 6000 angstroms, let's say, which is visible band. This is giving me some resolution, a number. If I want to match this number in radio, operating, let's say GMRT bands, which operates at 1 meter, what should be the size of the radio telescope? कुछ तो बोलो, कोई नंबर? हाँ? 300 meters? Hundreds of meters? Okay, and? Sorry? 10⁻⁷ meters, which is 1000 kilometers. Okay, very good. Then he is asking for the size of the Earth, a telescope of that kind, which is amazing. Okay, and it will be 8.3 kilometers to be exact. That opened your eyes, right? I'm just matching resolution which my eye is giving. Half a centimeter pupil when I want to do this thing. So it becomes very difficult when you want to do it in matching angular resolutions. Okay? Let's move to ultraviolet. So we are moving from radio higher and higher up. So these are short wavelengths, easily scattered by atomic gas and dust clouds. They put the hottest stars and ionized gas around them. For example, around matter spiraling, around massive systems essentially, which is kind of acting as a fuel, they get probed in UV. Similarly, Merit mentioned about supermassive black hole systems like active galaxies. Active galaxies are very hot, matter spiraling around them and falling onto them. The matter acts as a fuel. The temperature is typically 10,000 Kelvin, and that gets emitted in ultraviolet. So active galaxies, essentially, one way to detect these objects was initially that they show ultraviolet excess. Compared to visible band, they showed ultraviolet excess. This felt there was something happening over there. Next is the X-ray part over there. These are even more highly energetic systems. Highly penetrating. We have essentially come back from very low, very high penetrating to very low penetrating to back to high penetrating. And dust that you see in these systems is nearly transparent. So essentially X-ray can just go through most of the systems. These are typical probes of cosmic collisions. If you take two cluster of galaxies, like I'm not talking one galaxy, I'm saying one cluster of galaxy, another cluster, just bombard them. And we image this object in X-ray. Spectacular. It's fantastic to look at. And those are seen in X-rays. Similarly, now you can take it on a smaller scale, that to take two galaxies, just bombard them. And those temperatures are of the order of million Kelvin, and you will see it in X-rays. So then further, gas ejected at high speeds from rapidly dying stars, that's also seen in X-rays. Then, this I mentioned. Atmospheres of stars which are like corona, sun's corona is of the million Kelvin. That's also seen in X-rays a lot of times. So to summarize, most compact massive objects thought to be black holes, they display X-ray emissions. Corona of stars display X-ray emission, etc. This is a picture of Andromeda galaxy, one of our nearest neighbor, seen in different bands. So you have essentially radio, infrared, optical, ultra, X-ray, and even composite over there. So if I had shown you this X-ray picture of the same thing, it would have been boring. You wouldn't have liked it. So next, my thought is to talk about what emission mechanism is happening in these systems. We'll take it up over there. So this comes back to the same picture. Some people said that these are probing different energetic phenomena. One person said that these are images of the same source. Why do you think it should be same image of the same source? The locations are all very randomly placed unless I have shifted something, right? Indeed, these are image of the same source, and this is the composite bottom left image. What you see middle panel is the optical, which looks very boring. Bulk of the starlight is what is seen in various. So this is a cluster of galaxies. So starlight seen from the various galaxies is what is shown over here. This is cluster of galaxies, which means gases of each of these galaxies is getting interacted with another. So some kind of bombardment is happening that heats up the gas to million Kelvin, and that is what you see in X-ray over here, and this is a radio image of the same field. This is a remnant radio galaxy sitting in the periphery, which is being powered by supermassive black hole, a fuel falling onto it, making an active galaxy, which we'll learn tomorrow. And if you put all of these together, they're like spatially displaced, right? But they all look at the same thing in some certain. So what is happening, since this is top right image is made by me, this other image, X-ray image was made by collaborator, and we put all these things together. One of my favorite objects we'll look at, so this essentially is what this whole picture is. This little piece that you see in radio, so this is an active galaxy, matter falling onto it. The active galaxy is sitting in a cluster environment, so essentially it had a supermassive black hole at the center, matter falling on it. Because it's a gravitational potential energy, the jets spread out, they form radio lobes, which Neeraj was mentioning that they have fantastic symmetric lobes. If I take this object, and because it's lying in the cluster environment, it's moved. Center of the potential cluster is somewhere over here, and this is sitting over here, meaning it is moving in the cluster potential. So the two jets trail behind. They essentially form a core and a trailing jet-like feature, and that is what is happening to this system. Good. So having convinced you that if I want to see my favorite object in my favorite band I have to compromise because I need other bands to understand the object completely, right? But I still can stick to my favorite object. So we'll look at these other features over there. So I have talked about variety of objects seen in variety of wave bands and what is the emission mechanisms associated with it. I'll give you a flavor of that, and once we are, like you feel sleepy, I feel tired, we'll stop. Okay. Some of you may know this equation, the top one. That's called black body emission, where essentially Wien's displacement law comes using this. And if h times mu is far less than kT, then we are talking in the radio regime, they call the Rayleigh-Jeans limit. We talk about photons, right? When you look at an object and you put photomultiplier tube, you start collecting photons. In radio band, photons are very boring things, largely because the temperatures are very small. Just want to tell you, optical photons, 600 angstroms, they are talking about 2 electron volt, or the temperature is around 2000 kelvins. If I do the same thing at radio band, 1 meter is 12 millikelvin, I can't even detect it. So in radio, essentially a detection limit strategy changes completely. So what you say is you don't think classical, don't think of detecting photons in radio, you think it classical in terms of electric field. So you essentially say electric field which is falling onto some system, create the oscillations and carry the voltage signal out. That's how we detect the radio emission from these objects. Further, electromagnetic radiation is emitted by accelerated charged particles, and we also looked at the black body emission. The thermal emission depends purely on temperature of the emitting object, and that's a characteristic wave curve of black body emission. Non-thermal emission does not depend on temperature, so we'll look at these two separately. And we also know photon frequency is proportional to energy, so that is how we determine the energy for the radio photon. Typically, when we look at an object, you will essentially see variety of emissions. It can be continuum, it can be spectral line, or spectral line can be seen in emission or in absorption. So what exactly is happening is the following. You are having a continuous light source with some gas of cloud in an intervening medium, and then over there your telescope is sitting and you are looking at it. So if you would have looked at this directly, you will essentially see a fantastic brightness as a function of wavelength, some emission over there. You will put your telescope at certain band and essentially observe what is happening in that band over there. Because this object is, suppose there is an intervening medium between them, and this intervening medium may also this background object may not be there, then this intervening medium is going to show some spectral lines. But suppose this background source is there, you will see the spectrum which is continuum and spectral lines of the intervening medium. So that is a typical thing. So when you want to plan your experiment, you may want to study continuum emission, you may want to see particular spectral lines. So some person said that these are images, those three images which I showed are images showing different, what was it, I missed out, elements. So then essentially you are talking about these various spectral lines which are the characteristics of what transition is happening in that element. So that can also be done. Good. So we'll pick up black body emission and free emission in the next thing. So thermal emission is what I'll be picking up. So this is, solids are nicely packed, liquids are little loosely bound, gases are moving all around this. So any object with temperature above 0 Kelvin emits thermal radiation. And temperature is related to how the particle motion is happening over there. Temperature can also, if there is a molecular system, it can also affect the molecule motion. We will come to that later. And all molecules, because they are sitting in a temperature bar, they are in constant motion with one another. And atoms may have like 3 degrees of freedom, x, y, and rotation, spin kind of. But molecules, because it's a system which can have a linear system, can have more degrees of freedom. So when you look at such systems, molecules or atomic systems, you essentially have heat, temperature, and motion. And if you want to understand these things, you essentially cold gas will have less energetic, hot gas will be more energetic. And we'll try to look at this aspect next. This I've already talked. Let's come to this. So free emission I'll pick up first, which is what is happening is an electron in presence of an accelerating electron in presence of a massive ion. When it comes, it essentially changes its path. And when it changes path, it emits radiation. This is free emission. Both the ion has not got disturbed, the electron has only changed its path. They are not coalesced or made into different things. They are initially free, they are remaining free, and that's the emission which we are talking about in this system. So, and most of the visible universe, since it is diffuse at hot at temperatures of 10.4 Kelvin, then if they are not in thermal equilibrium, then typically what we will see is free emission in these systems. And I'll give you one example of this thing. This spectrum is almost flat in a free emission, but the moment it becomes optically thick, meaning the system can start absorbing its own radiation, then we will start seeing this curvature, which is black body emission. Because at low frequency, photons cannot escape, they undergo absorption. Once absorption starts, it will come to thermal equilibrium, which means it has become a black body emission. Otherwise, it's a flat spectrum. What kind of systems show free emission? So, for example, ionized gas around star-forming regions or active galaxies. So, solar flare. You are aware of solar flares. Great. I was surprised. People look blank when I use the word solar flare. The northern, what is the green light, right? It's because of solar flares. The temperature is 10⁻⁷ kelvins, and so if you look at free emission, in radio it is flat, and if you observe the same object, these solar flares in X-ray, you will see exponential decay over there. But both are free emission. S2 regions, which are singly ionized hydrogen clouds, they have a temperature of 100,000 kelvins. They again show radio emission flat, which I showed over there. Orion Nebula, 10,000 Kelvin in radio, again they show free emission of the order of 10⁴. Sorry, in the emission is flat. And more examples. Clusters of galaxies, which is again my favorite. The temperatures for coma cluster, the temperature is around 100,000 100 million Kelvin, and in X-ray it is flat, or occasionally you will see exponential. So the more hotter the system, the free emission essentially remains flat bulk of the time. We'll talk about this object again. So this is M82 galaxy, star forming galaxy. What you see, this magenta count are at magenta are at 2 centimeter radio image, and this green dots are at 7 millimeters radio image. This is all you see, and the background is a Spitzer infrared image for the source. And all this radio emission that you see is happening from the obscure regions. I said radio is very transparent. Even though it's sitting in an obscure system, radio emission can penetrate through. Just that in this system, the radio emission is happening at a very small locations, tiny locations. And all this radio emission is free emission. We'll move to spectral line emission. I'll skip these. I try to talk about one part of it, but I'll give you a flavor of what is happening, what kind of emission you see over there. So, atoms and molecules have different quantized energy states. You essentially can have stable configuration, then electron move jumping up to higher level, coming back. Once it comes back, it is going to emit a photon, and the photon I can detect. So it may jump up because it took some energy from there, or some collision happened or something. So when these things happen, they essentially measure frequency, strength, how energetic the thing was. With line width can tell me, line width and the profile of the line can tell me certain modes, like kinematics of the system. So they probe density, temperature, and relative abundance. 21 centimeters is one of the famous ones, we'll come to that. So what typically happens, suppose I have a molecule which is linear system, it can rotate. Faster rotating to slower rotating, this is rotational transition. This can happen. It can also vibrate. High vibrating state to low vibrating state, that's also vibration transition system that can happen. So, yeah. So, and molecular and vibration transition, for example, in silicon system, the silicates, the gas systems, you typically see in IR, and molecular rotation systems that you see mostly in radio band, and in optical you see most of the time electronic transitions. So, yeah. So this rotation and vibrations, what you see over there, essentially most complicated for the atomic lines, because you're talking about now two atom system. And radio line emission can come from both vibrational or rotational systems. ISM, the interstellar medium of our galaxy, half of its mass is in molecular hydrogen state. So then it becomes important that I understand this molecular hydrogen state in detail. So I want to understand the vibrational energies and rotational part of it. And about 1% of the cloud mass is dust, which causes extinction. So essentially, it will not allow you to see everything easily. Okay. And these have densities of the order of 10,000 per centimeters cube, temperature around 10 to 20 Kelvin. Nirachi did mention that what is happening over there. So, ALMA, the Atacama Large Millimeter Array in Chile, was built to understand these aspects. So they essentially had vibrational states which they wanted to understand on J equal to 1 to 0. This happens at this frequency. 2 to 1 happens at this. 3 to 2. So they made these systems and the detectors focused on these frequency states so that they can understand the rotational and vibration in the CO emission line. This was important because CO luminosity to hydrogen molecular mass was used to determine what's the fraction of total mass of the system. Yeah. I'll skip this radio combination lines. If you have questions, we can talk about it. Yeah. Next is 21 centimeter. This was also briefly touched upon by Neeraj. So, these are hyperfine transitions. Essentially, you have hydrogen molecule has one proton and one electron. When they are both in parallel spin, this is one state, and they move to another spin, this is another state. And the transition exactly happens at 21 centimeter, 1420 point something. megahertz. So very, very heavily studied large number of objects in 21 centimeters. So think of protons and electrons as spinning systems, as I mentioned, and from one state to another state. The spontaneous flipping is, the transition probability is very, very small. 11 million years one transition, but just the line of sight depth is, the integrated line of sight or the amount of hydrogen along the line of sight is so huge that this can happen shorter time scale. So it's a path length or the column density of the hydrogen which becomes important. This is hydrogen gas in different galaxy systems. Contours that you see is amount of hydrogen gas. So just take, okay, I don't know if you are familiar with how to read these contour images of galaxies and systems. What you see, you can say this is the brightest, this is second brightest, and the total extent of the galaxy as seen in 21 centimeter is what is displayed over here. These are fainter, these are brighter. So this is the host galaxy that you see in optical, but the 21 centimeter extent is huge. Similarly, this is the radial image of the galaxy, but the 21 centimeter is tiny over there. Optical host is still smaller than this. So I just want to make you feel that, compare the size scales. Optical host is usually smaller than the 21 centimeter extent. Radio continuum image may be much larger than that. And little bit of what happens, how people study this thing. So you essentially look at in units of brightness temperature. This is your telescope that you are looking at. This is a background continuum source, and this is the intervening cloud, the H1 emitting cloud or absorbing cloud, which is a temperature T and it has optical depth tau mu. So if you take this brightness temperature, what is observed, it will have contribution from the continuum and attenuated by this cloud over there. You do a little bit of math and you can come up with this little bit equation. So if what happens is essentially you can have, if temperature is greater than continuum temperature, then this is emission line, otherwise seen in absorption. And you can study, in terms of physics, you study the same thing, just that who is dominating whom can decide whether you see the system in emission or in absorption. This little feature is seen in stars, which is seen in optical because of the stars. This little trailing feature is completely seen in H1 21 centimeter. So some stuff is seen only in radio band or only in 21 centimeter spectral line. We'll skip this major emission. Right. We'll shift to non-thermal emission. We'll talk about synchrotron emission next. Okay. So, you know cyclotron emission, really fast moving electron in a magnetic field. If I make this fast moving electron to a relativistic speeds, meaning speeds close to speed of light, in presence of a magnetic field, that emission is called synchrotron emission. I have moved from cyclotron to a little more energetic phenomena. So that is what is synchrotron emission. This little person is Grote-Reber, father of professional astronomer, first professional astronomer, and based in the memory of his name there is an award called Grote-Reber Award, which essentially is part of little piece of his dish which he built by his own money in his backyard. And that first recipient of that award was Professor Govind Swarup, father of Indian radio astronomy, because of whom many of us have job. Who built Kalyan Radio Telescope, who built Udi Radio Telescope, who built Giant Microwave Radio Telescope. He and his team, and he was the brain person around that. So we'll look at these things. Okay, this slide is a little collage of variety of phenomena or emission that is happening. These red lines are typical synchrotron emission. They essentially have a power law. Orion Nebula has emission of this kind. I've just walked you through a little bit about various variety of objects. Now, Orion Nebula is star forming region. this part and then becoming flat. I just talked about it. What is happening in Orion Nebula? What kind of emission this must be? Yes, free is flat. So this flat makes sense. What is happening over here? Right, because it is optically thick over there. So, and then Crab Nebula, bulk of it is free, which is completely flat. Quiet Sun, which is again over there. So, purely looking at spectra of various variety of objects, these are all radio bands, 100 megahertz to 10 gigahertz. I can understand variety of phenomena that are happening, emission processes that are happening in these systems. We'll skip this. Cyclotron emission is also seen. This have just come. Yeah. Synchrotron emission, what is happening is power law. So essentially because the system is, if it's ensemble of electrons which have power law energy distribution. So if I take one electron, it has its own energy distribution and different, it has energy from E to delta, E plus delta E, variety of it. The turnover for each of them happens at different frequencies. So if I take an ensemble of electrons and try to fit the peak of all of them, then this is what comes out to be. So the synchrotron emission characteristics is power law. As you go lower and lower frequencies, the flux density increases, unlike free emission. And of course, again, if it is self-absorbed, the system is so heavy that emitting electrons can again absorb the radiation which is coming down, then we may see feature of this thing. Though this is spectrum of a single electron, you can see certain objects of those kinds also. It may look free, but it is not. Now when I talk about variety of objects, just because I am seeing in different band doesn't mean that synchrotron emission cannot happen at very high energy or at visible bands. This is image of Crab Nebula. It's synchrotron emission seen in radio, infrared, optical, X-ray. If I make image, and these are all at comparable resolution. The Chandra telescope has been operating for 30 years. Gives a resolution of half arc second. This is radio image from the LA, half arc seconds. These are again optical is half arc second and Keck is again half arc second. So matched angular resolution, I stated, right? I want to have two apples to apples comparison. I don't want to have apple and a pumpkin comparison. Doesn't work out. Huh? And these are all showing the synchrotron emission. Synchrotron emission has a drawback, like high energetic electrons get depleted very fast. Like lifetime of X-ray emitting electrons is just 1,000 years. After 1,000 years, it just die down. Which means 10 generations down the line, this object may not be there. Certain we may come back and say that our forefathers were looking at objects which was completely obscure. It doesn't make sense. Huh? So at more and lower frequency, the energy, like essentially energy gets peaked. So this will stay. This lifetime is of the order of million years, hundreds of million years, but this energetic lifetime is just 1,000 years, and you can scale it from this far side to near side. You can also see in radio galaxies. This is an example of radio galaxy. You see, this is radio image of at very high angular resolution. This is the same image over here at 2 centimeters. This little patch is what's shown over here. This little patch further is sitting over here. And so I move to lower and lower frequency. This is 20 centimeters, this is 90 centimeters. Meaning lower and lower frequencies, I am seeing physical appearance of the source different and different. In this, again, I can pick up core and A, B, C, D, various these things and ask a question, how is the spectra of these things coming out to be? That also can change. So this is core and various knots that you see over here. The spectra is changing over there. This is telling us that the farthest piece over here is the oldest population, and this is the slightly old, slightly younger, much younger, youngest. So purely looking at the radio source at different bands, making a spectra of this thing and asking a question, what is happening over there, you can tell us a little bit, several variety. This is also a radio galaxy. The core is sitting over here. Supermassive black hole is sitting over here. It's emanating out jet, forms the radio lobes. The matter further diffuses to form the wings-like feature over there. At various locations, over here, I can pick up, or I could have done it like this and ask how is the spectra looking like. This is farthest most, which is steepest. This is central, which is a little bit, and this is flatter further. So this is telling me that the near to the core things are younger, farthest from the core these are older, which is normal, right? Everything is happening at the center. As it moves farther and farther, it becomes older and older. Okay, I want to give you a perspective of energetics of this little source. So this is one of the Cygnus here source, very famous. If you just Google, you will see a fantastic first radio galaxy imaged using just single baseline interferometer. Geometry is 30 antennas. How many baselines it will give me? 30 C2. What is this number? 435 baselines, 435 interferometers. This object's very first when it was imaged was just one interferometer. And they could say that this source should have a size of these things or identically placed with respect to the center. That was a thing. This source has a flux density of 2000 Janskis at gigahertz frequencies. Now I just want to put how energetic this source is. So we'll take these numbers down the line. So if I take this flux density or this frequency and do little, I also know the distance to this source, which is around 230 megaparsec. I can determine the luminosity. That number is around 2 to 10 power 42 ergs per second. This is at 1 gigahertz frequency. If I want to detect the total amount of luminosity stored in radio band, then I have to integrate from 10 megahertz all the way to 100 gigahertz, the complete radio band. That number is over here. Next, I can ask is a synchrotron emission, which is because of relativistic electron moving in the magnetic field. I can say that energy density of electron population and magnetic field energy density, these are kind of equipartition, balancing one another. If I take this assumption, then I can determine the minimum magnetic field it should have, or minimum energy it should have. I have to do a little bit of integration also. Fortunately, many of you have written JEE, so you know what integration is. These are the numbers which will put up over there. If I take care of this little pieces, I have not added this eta is, should I consider this plasma to be neutral? There is electrons, positrons, or electrons and protons. Protons are heavier, they will not get transported to electrons distances quickly. So I don't know that composition of material that I am seeing. I don't know much about the composition of electron, proton, positron, what this is. So that assumption I have to make over here. If I play with that assumption, this number will be around 30 to 300 microgauss. Similarly, in energetics unit, this will be around 10 power 59, 1 to 80. Now we'll take this Einstein's equation and ask a question. Okay, if I have 10 power 59 ergs and E min upon C square is all that I want to determine the mass of the system which is responsible for this. That number comes out to be 3 million solar masses. And I know fission process, this Einstein's equation is just 1% efficient, meaning out of 100 units only one gives me this energy, which means the mass of the black hole system in this has to be 300 million solar masses. $300 million times the mass of the sun is what this system is power. These are called supermassive black hole. We'll look at them tomorrow a little bit more. I'll talk one more emission mechanism. Are you tired? I can stop here also. It's fine going, right? And we have energy. And I can hold a little bit with myself. So what is inverse quantum emission? It is essentially low energetic electron coming in presence of electron gets excited with a high energy. In the rest frame of the source, this is just electron scattering, the Thomson scattering that you studied in your textbook. It's not different, just that in observer's frame this becomes a inverse compound emission. Okay? Yeah. I didn't want to cover propagation effects. This is the next step. Essentially, you want to detect this little piece over here. This gets modified by various parameters when it comes from there. You have scintillation, this is your emitted signal. You essentially have huge path length between source and me, which causes dispersion, the scattering. If you are looking at the magnetic field part of it, so essentially the right circular and left circular will travel differently in the magnetic ionic medium. They'll give me a rotation measure, and everything is sitting in. I'm an engineer, I'm not an engineer, I'm an astronomer, but I like doing a little bit engineering. If engineer has given me a little bit defective instrument, then instrumental noise is also sitting over there. And I should be able to correct everything to get the Nobel Prize, huh? Fine, then I'll skip this. Good. So we'll bring all this together. I'll give you a flavor of those things. So typically in radio, the meter, 2 centimeter and millimeter, use what are the dominant things? 21 centimeter line. They look at the neutral gas. Hydrogen recombination line, I didn't talk about it. Then a lot of molecular lines that tells us about the dense molecular gas. Rotational lines that again tells you cold molecular gas. This is a spectral line in this band. If I would have been looking at the continuum, free flow emission we talked about, which comes from H2 regions. Synchrotron emission is like extragalactic active galaxies, jets, lobes, hotspot, supernova also, cosmic ray electrons and presence of magnetic field of normal galaxies also show that. I didn't talk about it. Then thermal emission from dust, that cold and dense gas. If you're looking in the submillimeter and far infrared, then molecular rotation lines can tell us about the warm, dense gas. Solid state features like silicates or dust is what it will tell. Then radio recombination lines. I don't know if you remember the hydrogen Rydberg number, Rydberg. So one transition can happen from the another. Those are the recombination lines. And in thermal emission, you typically put warm dust over there. I'll give you a little bit example about what is happening at various, putting this together. Sun is the nearest star, nearest object, and still a very complicated. It gives you a variety of phenomena. This is spectrum of sun, plasma frequency is what is put up over here. This is the data over here. This is the height above solar radii and frequency. If you want to study corona, the plasma emission is what becomes important. If you go a little bit lower heights, you will see plasma and brainstorm emission, then brainstorm and then gyrosynchrotron, which is between synchrotron and cyclotron. I'm coming back to this object again, the M82, which is a Stardust galaxy. And so this was a 2 centimeters, this was a 20 centimeters and 2 millimeters emission. And the spectra of this, integrated spectra of this system is what is shown over here using this data. We'll try to model this data using various variety of emission mechanism. So this little piece is mostly because of cosmic ray electrons, which is synchrotron emission. The blue part is dust heated by usual photons, which is black body over there. And the greenish part, I have to put in my hand, is mostly free emission. And if I put all of these together, sum, the synchrotron plus free plus black body, that's how I'll be able to construct this. And there is a little bit bend over here, which is essentially because of synchrotron self-absorption. Like when the same electron emitting region can essentially absorb the system. Another example, this same radio galaxy, the Cygnus A, for which we determine how much was the mass? 100 million solar masses. It's a big number, huh? One followed by many zeros. So this is what you see in background is optical, what you see in red is radio, and the blue is X-ray using Chandra, all at matched resolution. If I want to map, like take the spectra of radio, this hotspot over here, and these are the little data which is shown over here. This is from the optical, what is limits over there, and put up over here. So this is the model of the spectra as seen in observations. Now I'm asking this X-ray emission seen at these locations, this data is sitting over here. I want to model if this is inverse quantum emission or like synchrotron emission. And so this is inverse quantum, this is synchrotron. Indeed, this is synchrotron emission that you see in X-ray emission from the hotspot of radio galaxy. This is not always true. If I do the same thing in 3C390.3, another radio galaxy, then my whole thing sits far below, and this is essentially what I end up over here. So different objects will show different things over there. This was what I was missed out earlier and complete it over here. This is Whirlpool M51 galaxy. What the ticks that you see over here are all magnetic field emission, telling us how the magnetic field emission is large scale. And this radio contour that you see is radio image of the source, and the background is optical. So this is mostly because of cosmic electrons which are permeating this system. This is synchrotron emission, and length of the lines is telling us how strong the magnetic field is. This is very difficult experiment, not too many examples exist. This is one of the well-studied system which is talked about. And so this is one thing. So I gave you some flavor of multiwavelength astronomy with examples of what emission is happening in various objects, depending on your favorite object, what instrument to target, or if the instrument doesn't exist, what instrument to build, observe that target, and then do your science.